Okay students, so in previous class we discussed about geometrical isomerism of coordination compounds. Geometrical isomerism of coordination compounds. In this class we are going to discuss CFT, crystal field theory. Then we will discuss weak ligands, strong ligands, spectrochemical series. Okay, crystal field theory we are going to discuss. Very important, so carefully listen to me. Crystal field theory, it is nothing but a CFT. CFT we are going to discuss. Okay, see what is a CFT means. First of all, you know students, see here, if the coordination complex contains 6 ligands, then coordination number is a 6, then the geometry of the molecule is a octahedron. Geometry of the molecule is a octahedron. Okay, see, repulsions can be erased between the central metal atom having electron pairs and a ligand having electron pairs. Due to repulsion between the central metal atom and the ligands, so d orbital can be split up into 2 sets. D orbital can be split up into 2 sets. Okay, EZ and T2Z. This type of splitting of d orbital is nothing but a crystal field splitting. Crystal field splitting. Okay, crystal field splitting. Now, crystal field splitting in octahedron complexes. Crystal field splitting in octahedron complexes we are going to discuss. Okay, so crystal field theory means how crystal field splitting can takes place in d orbital we are going to discuss. See students, if coordination number is a 6, if coordination number is a 6 in complex compound, if coordination number is a 6 in complex compounds, then ligands equal to 6. So geometry is octahedron. Octahedron. Due to repulsions between d orbital of central atom and ligands, due to repulsions between central atom and ligands, d orbital can be split up into 2 sets. Due to repulsions between central atom and ligands, due to repulsions between central atom and ligands, d orbital split up into 2 sets. D orbital, d subshell or d orbital split into 2 sets, EZ and T2Z. Eg and T2C. Okay. Here due to presence of ligand, d orbital can be split up. This is nothing but a crystal field splitting. The splitting of d orbital, the splitting of d subshell in presence of ligand, in presence of ligand is called crystal field splitting. Crystal field splitting. Okay. Now we are going to discuss crystal field splitting in octahedron complexes. Splitting of crystal field in octahedron complexes. Okay. If the coordination number is 6 in complex compounds, then ligands are equal to 6. So geometry is a octahedron. Due to the repulsions between central atom and a ligand, d orbital split up into two sets, Eg and T2C. The splitting of d orbital into in presence of ligand is called crystal field splitting. Crystal field splitting. Okay. See here, it is a ligand, it is a central metal atom. Okay. It is a octahedron geometry. So ligands, central metal atom, it is a metal atom plus 6 ligands gives rise to, it is a metal, these are ligands, and it is a octahedron geometry. Octahedron geometry. Okay. So these two are in axial, these four are non-axial. These two are in axial, these two ligands are in axial, and these four ligands are non-axial. Now splitting, crystal field splitting in octahedral complexes we are going to discuss. Crystal field splitting in octahedron complexes. Crystal field splitting in octahedron complexes we are going to discuss. Okay. See here, it is a d orbital. It is a d orbital. 1, 2, 3, 4 and 5. Okay. So it is a average energy of d orbital. Average energy of d orbital. Okay, then split up due to repulsions between the ligand and d orbital. 1, 2, 3, 4 and 5. Here it is dxy, dyz, dxz, dx square y square and dz square. These two are in axial and these three are non-axial. Okay, see here. Okay, it is easy, it is T2C. It is easy, it is T2C. Okay, so here it is 3 by 5 delta naught, it is 2 by 5 delta naught. This total is nothing but delta naught. Okay, it is a 2 by 5 delta naught, it is 2 by 5 delta naught, it is a 3 by 5 delta naught. So these two orbitals goes excited state and these three orbitals, it is splitting of d orbital. Splitting of d orbital. It is nothing but a crystal field splitting. Crystal field splitting. Here delta naught equal to stabilizing energy. See here, delta naught equal to stabilizing energy. Stabilizing energy. See, if delta naught is more complexes, if delta naught is more, then complex is more stable. Then complex is more stable. Okay, this is nothing but a crystal field splitting energy, crystal field splitting energy or stabilizing energy. It is called crystal field splitting energy. Crystal field splitting energy. Okay, CFSE, crystal field splitting energy, that is called crystal field splitting energy. Delta naught is a stabilizing energy or crystal field splitting energy. See here, is delta naught is a more, then complex is more stable. Crystal field splitting energy is nothing but a, if crystal field splitting energy is more, then complex is more stable. If crystal field splitting energy is less, then complex is less stable. Okay, this is based on field strength of ligand. Based on field strength of ligand, then ligands can be divided into two types: weak field strength ligands and strong field strength ligands. Okay, that is a different. So it is nothing but a crystal field splitting. So crystal field splitting of octahedron, it is a d orbital, average energy of d orbital, then it is nothing but a splitting So he having easy two sets dxy and dyz. Here it is d x square y square and d z square. It is d xy d yz d zx. Okay, split up into two sets. So this is nothing but a crystal field splitting. Why splitting can be takes place means due to presence of ligand, due to repulsions between the ligand containing electrons and central metal atom containing lone pair of electrons. Okay, so if ligand is strong, then crystal field splitting is more. If ligand is weak, then crystal field splitting is weak. Okay, so this is nothing but a crystal field theory. So it is nothing but a crystal field splitting in octahedron complexes. Okay, it is the shape. Ligand metal, 6 ligands are in step octahedron geometry. Now crystal octahedron complexes, this type of crystal fielding can be takes place. Okay, now we are going to discuss based on field strength. See here, based on field strength, we are going to discuss types of ligands. Here, based on field strength, two types of ligands we have: weak field strength ligands, strong field strength ligands. Okay, see here, based on field strength, ligands are two types. Ligands are two types. Okay, the first one, strong field strength, strong field strength ligand, strong field strength ligand, and second one, weak field strength ligand. Okay, based on field strength of ligands, okay, based on field strength, ligands are two types. Okay, see here, Based on field strength, ligands are two types. Okay. So based on field strength, ligands are two types. First one, strong field ligand, strong field strength ligand, strong field strength ligand, and weak field strength ligand. Okay. See here, strong field strength ligands means see, ligands are more field strength. So these ligands are more field strength, these ligands are more field strength means stabilizing energy is more. Okay, here these ligands are weak field means less field strength, less field strength. Okay, these ligands are less field strength. Okay, strong field ligands means see, these ligands are more field strength. Strength less field means stabilizing energy is less. Okay, here rearrangement of d electrons takes place. Rearrangement of d electrons takes place. Here rearrangement do not takes place. Rearrangement do not takes place. Rearrangement means, see here, d orbital is there. 1, 2, 3, 4. 1, 2, 3, 4. This type of unpaired electrons are there. Okay. If ligand field strength is more, then what happened? It can't jump to higher energy level. So here it can be rearrangement like this. 1, 2, 1, 2. This type of rearrangement can be takes place here. Here rearrangement does not takes place here. Okay. Next it forms inner orbital complex compounds. Okay. These ligands form inner orbital complex compounds. Okay, these ligands form inner orbital complex compounds. For example, DsP2 like this. Inner orbital means D is in the beginning. D is in the beginning. Okay. These orbitals, these ligands These ligands form outer orbital complex compound. Okay, outer orbital means D is in the ending. For example, sp3d. Okay, understand, here D is in the beginning means inner orbital complex compound. Here D is in the outer means ending means outer orbital complex compound. Okay, next these ligands delta naught is greater than P. Delta naught is greater than P. So here P means pairing energy. Delta naught means a stabilizing energy. Delta naught equal to stabilizing energy. Stabilizing energy. Okay, here these ligands delta naught is less than P. These ligands have delta naught is less than P. It is greater than P, that is less than P. Okay, these ligands have delta naught is less than P. So these are nothing but strong field ligands and weak field ligands. Understand, strong field ligand is present in the complex compound, stabilizing energy is more. Weak field ligand is present in the complex compound, stabilizing energy is less. Okay, then you have to know spectrochemical series. Okay, so what is a spectrochemical series means? Based on CFTE of ligands. See, the arrangement of ligands of their increasing order of CFSE is nothing but a spectrochemical series. Okay, the arrangement of increasing order of the arrangement of ligands of increasing order of ligands of increasing order of their CFSE, crystal field spreading energy, is called spectrochemical series. Spectrochemical series. Okay, see here we may say example for strong field ligands. We may say example. Okay, so here NH3 En Cn minus CO, all these are strong field ligands. Okay, here we may say example for weak field ligands, I minus, Br minus, next S minus 2, next SN minus, all these are weak field ligands. Now the arrangement of ligands of increasing order of their CFSE is called spectrochemical series. Okay, now these ligands we are given a order based on their CFSE, crystal field splitting energy. You will get a spectrochemical series. Okay, it is represented as see first one I minus is less than, Br minus is less than, then S minus 2 is less than, SCN minus is less than, and so on. Okay, see here, NCS minus is less than, next NH3 is less than, then En is less than, then Cn minus is less than CO. Okay, these are weak field ligands and these are strong field ligands. Okay, I minus, okay, I minus, Br minus, S minus 2, Sn minus are weak field ligands. See, NH3, En, Cn minus, CO are strong field ligands. So you will get a spectrochemical series. Arrangement of these in the order of their CFSE, then you will get a crystal field spectrochemical series. It is very important. Okay, so this is also based on field strength. So ligands can be divided into two types. So ligands can be divided into two types: strong field strength ligands and weak field strength ligands. So here on arranging CFSE, on arranging the order of the ligands, increasing order of their CFSE, then you will get a spectrochemical series. See here, the arrangement of ligands in increasing order of their CFSE is called spectrochemical series. It is represented as like this. So I minus, Br minus, S minus 2 less than Sn minus, I minus iodide, Br minus bromide, S minus 2 sulfide, Sn thiocyanate, here NCS isothiocyanate, next NH3. Okay, then if you want to write Sn after that, Cl minus, see here, is less than, Cl minus is less than, then N minus 3 is less than, then F minus is less than, then OH minus is less than, C2O4 minus 2 is less than, H2O is less than H2O. Okay, then NCS minus, like this. Okay, it is ligands, all these are ligands. Okay, then here less than, less than, less than, less than. Okay, here it is less than, less than, less than. This is nothing but a spectrochemical series. It is a strong field ligand, it is a weak field ligand. So based on the crystal field splitting energy, so here field strength, strong field ligand and weak field ligand. For a strong field ligand, crystal field splitting energy is more. For weak field ligand, crystal field splitting energy is less. Crystal field splitting energy more means so it can't jump, so pairing can be takes place in electrons. Crystal field splitting energy is less means so it can jump, pairing does not takes place. Okay, so this is today's chemistry class.